Now in this video we're going to look at superposition, the principle of superposition, formation of stationary waves, differences between stationary and progressive waves, as well as stationary waves in strings. Without much further ado, let's get started. The principle of superposition can be well thought of and well studied if we consider two waves. One is moving to the right and the other wave is moving to the left. Now the wave that is moving to the right is being shown by one arrow, and the other wave that's moving to the left is being shown by two arrows. Now when these waves they meet together with time, so the time is going down, so with time they're going to meet together, and then as you can see the amplitude increases. So we are saying the amplitude here plus the amplitude there is going to give you the resultant amplitude, which will be the summation, the algebraic sum of the two amplitudes. And then afterwards, this wave will go to the right, and then the other one will proceed to the right, the other one to the left, the other one proceeds to the right. And similarly, if you have got these waves, right, that are moving, and initially the two waves have they are 180 degrees out of phase with each other. So the first ones were in phase, as you can see, crest meeting crest. Now crest is going to meet trough, and when this happens, there's going to be cancellation of the two displacements from the waves, and then after that the wave that was moving to the left continues moving to the left, and the one that was moving to the right continues moving to the right. So two pulses in phase produce a large pulse, which is the sum of their amplitudes, as you can see, where they cross or superpose, while two antiphase pulses produce zero displacement, as you can see, zero displacement there. The principle of superposition, it states that wherever two or more waves meet, the total displacement is equal to the sum of the individual displacements at that point. So whenever two or more waves meet, the total displacement is equal to the sum of the individual displacements at that particular point. The principle applies to all types of waves, transverse or longitudinal, e.g. water waves, sound waves, but the waves must be of the same type, e.g. two or more sound waves can superpose, but a sound wave and a water wave will never superpose. So the two waves must be of the same type. The second part of the principle also is shown above, namely that the waves pass through one another without affecting each other. So the waves, as they pass through, they don't interact to deform one another. So this wave, as it emerges from the point of meeting or convergence, when they meet, the wave that goes to the right or to the left will continue moving to the left without having been deformed in its shape. So the shape remains the same. So if there were particles, then obviously you know that with inelastic collisions, you expect for an inelastic collision to have deformities on the part of the one of the waves. But now, since they are waves, they do not have mass, and they won't affect each other, thereby changing each other's form or shape. Right, so they emerge from crossing with the same shape, momentum, and energy. This is different from the behavior of particles. Water waves in a ripple tank pass through one another without affecting each other, but two balls colliding would not be able to do so. Right, so I think I do have something to show on these waves. Okay, the stationary waves. Right. Right, so two, there's cancellation of the displacements here. So cancellation of the displacements there. Now where this one is at zero displacement, this one is maximum displacement, we see that the resulting displacement will be downwards, okay, not up. All right, that's it. Right, moving on. So the diagram now below shows how two progressive waves from stationary wave can be formed. Okay, two progressive waves from a stationary wave can superpose. Okay, two progressive waves form a stationary wave. How two progressive waves form a stationary wave. The red wave, which is wave A, moves to the right, wave B moves to the left. Each diagram shows the positions of the waves A and B a quarter of a period later. The resultant wave at these times is shown in black. So the resultant wave is the black one. The resultant displacement is always 0 at points N and maximum at points halfway between these points. So like I said, wave A is moving to the right, wave B is moving to the left, and the resultant wave is shown in black, as you can see. So here crest meets crest, so there's going to be reinforcement, so you find that there's going to be maximum displacement there. Here again trough meets trough, so we're going to have maximum but negative displacement, so you get this. So this is the stationary wave that is formed when t is equal to 0. Okay, right at the beginning you've got the stationary wave, the black one. Now in the time of t over 4, which is the quarter of a period later, you find that crest is now meeting trough and the resultant displacement is 0. So the stationary wave that you see will be that, and then comes back to 0, and then since this was 0, t over 4, now this is t over 2. So at t over 2 we're now seeing crest meeting crest again, and we have that form of a stationary wave. And then 3t over 4, you have this one. So 3t over 4 will have the same as the t over 4. And then at t, it will be exactly the same as at the beginning when t was equal to 0. Okay, so we have these points of permanent 0 amplitude, permanent 0 displacement. Okay, 0 displacement. And then in between the two nodes, you have two of these places, we do have maximum displacement. So these points of permanent 0 displacement are called nodes. So at these points the two waves always cancel out, so there is no movement. Then in between there, where you have the maximum amplitude or maximum displacement rather, we have antinodes. So these antinodes are places where the waves interfere constructively and make double height wave. So this word now, constructive superposition, we have constructive interference and destructive interference. So in constructive interference, crest meets crest. Destructive interference, crest meets trough. Okay, the distance between two nodes or between two antinodes is half a wavelength. So the distance between this node and that node, that's lambda over 2, half a wavelength. Then and again another lambda over 2, so which means that the distance between here and there will be a full wavelength. Okay, again the distance between a node and an antinode is lambda over 4. Okay, since this one to there, between two nodes, it will be lambda over 2, so it should be lambda over 4 plus lambda over 4, which is lambda over 2. So the distance between a node and the next adjacent antinode is a quarter of a wavelength. Now let's look at differences between stationary and progressive waves. In a stationary wave, the wave shape does not travel along the string. As you can see, it always changes from maximum to 0 to the negative maximum, then to 0 again, and then so forth and so on. Whereas in a progressive wave, the waveform advances with the speed of the wave. In a stationary wave, the amplitude varies from 0 at the nodes to a maximum at the antinodes. So there is zero energy at the nodes and maximum energy at the antinodes. Whereas in a progressive wave, all the particles vibrate with the same amplitude as the wave passes. No energy is transferred in a stationary wave. The wave energy stays at same positions along the string, or along the whatever is produced in the stationary waves, because the nodes and antinodes are at fixed positions. Okay. But we know that in a progressive wave there is transfer of energy from one place to another. There is energy translation in the direction of travel of the wave. Okay. All points between two adjacent nodes move in phase with one another. Points separated by one node move out of phase by pi radians or 180 degrees. So all adjacent points between two nodes, they all move in phase. Let's go back to there. So which means the points that are, so this is a node, this is a node. All points that are within this parameter all move in phase. All those that are between here, they all move in phase. Here all points move in phase, all in phase there. So these points and these points are exactly 180 degrees out of phase. These and these are also 180 degrees out of phase, or pi radians are out of phase. Now in progressive waves, all particles within one wavelength have different phases. As you remember, the formula for finding the phase difference, we said 2 pi x over lambda, so which means every point will be a different phase with the other. So as long as you can calculate the distance x and then divide by the wavelength multiplied by 2 pi to get it to radians, you get the different phase or the phase difference for each particular point between 2 points. So that's a difference with the stationary wave. Then the fifth difference is that the distance between nodes or between antinodes is lambda or over 2 or half lambda, whereas the distance between adjacent particles moving in phase is 1 wavelength. Okay. Now the next thing, or the last thing that we're going to look at in this video is stationary waves in strings. Stationary waves in strings. Stationary waves in strings can be achieved on a string by in tension by fixing both ends and making the middle part vibrate by plucking it, so progressive waves travel towards each other, reflect at the ends, and then pass through each other. Or by fixing one end of the string, sending progressive waves along it from other end using a vibration generator. Okay, so here we've got a signal generator there. Signal generator connected to a vibrator. The vibrator moves up and down, up and down. Then when this happens, the string starts to vibrate to form a progressive wave. Now there's going to be a reflection over there of the progressive wave, and then the superposition of the two waves results in a stationary wave. Now the mass here is there to provide tension to the string so that we can form different types of stationary waves. there. You can see, or you can observe different types of stationary waves, or you can adjust the tension in the string. Okay, the tension in the string. The vibrator sends progressive transverse waves along the string to the fixed end, where a phase change of pi radians, or 180 degrees, occurs. The reflected waves from the fixed end superpose with the incident waves to form a stationary wave at certain frequencies. Okay, at certain frequencies. So this is going to vibrate, and then we're going to have superposition there, forming a stationary wave. Okay, so I have something that I can demonstrate again on there. Let's see. It should be that. A section, and make sure that you do understand everything that has been covered here. Signing out.